All right, welcome to Chapter 8 on failure. We're going to be looking at several modes of fracture in this chapter. And first thing, make sure that you do, like all chapters, is go ahead and look through the learning objectives. There's 9 of them for this chapter, and we should be covering all of them. So when you're going through your reading, make sure that you can describe all 9 of these. Today, we're going to um, this first video, we're going to go ahead and look at 5, which are some impact fracture testing techniques. We are going to focus on the sharpie impact testing method. And in your reading, you can go ahead and look at the IZOD method, which is very similar, just has a slight difference in the sample holder. All right, so let's go ahead and get started. So first thing we want to do is just describe strength versus toughness. So we've been talking about strength in the previous chapters. And when we speak about strength, we're talking about yield strength and tensile strength. Mainly when we say strength in just a loose term, many people are thinking of yield strength. But strength is defined as the resistance of a material to plastic flow. A toughness, on the other hand, is described as the resistance of a material to the propagation of a crack. So if we have a crack present, the question is, does that crack blunt out and not continue to grow, or does that crack continue to grow rapidly and get fracture? And so that's the difference between a tough behavior, say in this case, where we get a lot of plastic deformation, we can absorb a lot of energy, and brittle behavior in this right case, where once we hit the stress value before we even get to ductility, the sample just cracks. So at this point, you should have watched the Sharpie impact test video in your playlist prior to this lesson. If you haven't, go ahead and pause here and go watch that, and then come back. So here's just some examples of some Sharpie impact test samples after they've gone through the machine. The sample itself looks something like this here on the right, with a V-notch in the sample, and then that force comes down and hits the back of this and causes the fracture. And you can see that just from the surfaces after the fracture, so here's that V-notch, right? These two samples are the top and the bottom, say, of the specimen. So here's the bottom, say here's the top. And you can see this behavior looks very brittle. Right? We're keeping all the nice sharp corners of the cross-section of the sample. You don't see any changes in cross-section. You get a nice flat fracture right across the sample. Okay, now as you start moving into these steels with different ultimate strengths, now remember, as the strength of a material goes up, or in this case, let's say as the strength goes down from 1550 to 950, remember what we do is we're getting an increase now in the ductility, the percent elongation. And you can see that in the samples, right? For the 1550 case, this is fairly flat. You're just getting some plasticity there on the edges. You can see it here on the other side of the sample. And you drop the ultimate strength and increase the ductility, you can see a lot more ductile tearing on that sample. So you're seeing that ultimate strength goes down, your ductility measure, percent elongation, goes up. Okay, so we can see that right in the samples. So here's what the data looks like that comes out of the Sharpie impact tester. If you've watched the video, then they've gone through and they've explained exactly how this energy, this impact energy, is measured. And so again, you want to watch that video. But this impact energy is the energy required to cause failure in the sample. How much energy did that sample absorb during the failure process? Okay, so the higher energies would be your ductile samples, very low energies, would be brittle. And we can have some cutoff energy. This is, say, about 20 joules. This represents a cutoff where below this value we can say that the material is brittle, and above the value it's ductile. So it's a good way to represent the ductile to brittle transition in a material. So each of these curves here, each sample is taken at a different temperature. So when we do have a transition, you can see that at the higher temperatures, we're getting a ductile behavior, high impact energy. And then at low temperatures, we're getting brittle behavior. And that's always the case with ductile to brittle. It's always the low temperatures that cause the brittle behavior. And then we have some transition period between the two. And since that transition period is wide, there are many options for choosing where you call the ductile to brittle. Sometimes it's referred to as kind of like the inflection point here. Other times a value is picked, and I'm going to use that this time, of 20 joules. And then ductile to brittle transition then is just that point there on your curve. And so for this one, it might be something like minus 27 degrees Celsius. Okay, and that's what they're saying over here for this A36 steel. Now, if you look at the Titanic, there's transverse and longitudinal directions. You get different properties depending on which direction you're looking at. And that's what's a result of the rolling of the sheet. It tends to change the orientation of the grains. And so it results in different properties in different directions of the sheet. But if you look at either of the directions on the Titanic steel, you can see that for this impact energy of 20 criteria, we're getting ductile to brittle transitions of about 50. In this one case, I think when you do it carefully, they get 56, and we get about 32 for the longitudinal direction. Okay. Now that's a big problem. 32 degrees and 56 are pretty high in temperature. And the Titanic, when it was sailing, was at minus 2 degrees. So it was way down here, way below the ductile to brittle transition. So you're basically looking at a brittle steel. And so pretty much anything it hit, it was going to crack. Right? Modern steels like A36 maintain good ductility down at these low temperatures. All right. You can read more about that if you want, if you can grab this Journal of Metals article. You can look up most of this information on the web as well. Okay, so steels, one of the principles we'll see, especially in the next chapter, is that we'll see that as the carbon weight percent in a steel, right? Steel is iron carbon for plain carbon steel. That's what we're talking about here, so we don't have to worry about other alloying elements. But the carbon weight percent that's in that steel, as that number increases, we're actually increasing the hardness of the steel. So that goes up. This is the carburization example for a gear, right? We wanted to increase the carbon content in the surface, and that was to increase the hardness. We know that hardness is correlated to strengths. So yield strength goes up, the ultimate or tensile strength goes up with the carbon. Okay. Now, of course, the trade-off we know is that the percent elongation or the ductility measure would go down. And now we're also seeing that the ductile to brittle transition, or the impact energy here, is also going to be negatively affected as we increase carbon content. So here we have a low carbon content. All right, so low carbon content. And we can see, let's just go ahead and stick with that sort of 20 number here. For the impact energy, you can see we get a ductile to brittle transition for this low carbon content down around minus, what's that look like? Minus 75 degrees Celsius. So that's a good low transition temperature for a low carbon steel. Right? So this one has a lot of ductility, and then we also get a good, again, ductile to brittle transition. And this transition looks fairly sharp, and we get a very ductile material when you're looking up here on the other side of the transition. But now notice as we start adding more and more carbon in here, okay, weight percent carbon, we're going to start getting to the point at 0.6 weight percent carbon, where even our maximum impact energy is very low. Okay, so this is a high strength steel with a high carbon content. But again, the ductility is going to be very low on this, and the impact energy for failure is also very low. Okay, so again, this is now going to be another trade-off, meaning that the toughness of this material is going to be very low. And if we stick with the 20 mark, then maybe we could put some transitions somewhere up here, but you can see it's very high in temperature. And there really isn't a lot of a transition because it's already practically brittle. Okay, so with the Sharpie impact test, again, make sure you watch that video. What we were looking at again is the energy to fail a sample, how much was absorbed in the sample during the process. It works very well as a quick test. You can do ductile to brittle transitions as the temperature is changing on the sample, but it doesn't allow us to give quantitative numbers and to really define a material property. It just allows us to find things like ductile to brittle and relative toughness between different materials. And so what we would like to do is we need to get some kind of a toughness property so that we can actually make predictions and calculations on fracture. And so what we're going to do is we need to get into a little bit of fracture mechanics and talk about that. So next time we'll jump into the fracture mechanics.